Okay, last time we started talking about vector fields. So initially we introduced the notion of a vector field, but it had a very narrow focus at that time, and that was just to provide us with the notion of these basis vector fields. And last time what we saw was that vector fields are connected to ordinary differential equations, in the sense that when you represent the notion of an integral curve for a vector field in a set of coordinates, then that condition for an integral curve becomes exactly the condition for the existence of a solution to an ordinary differential equation. Okay, so we talked about that last time, and we talked about integral curves and flows and things like that. Now we're going to look at vector fields from a completely different angle, and that's one of the interesting things about vector fields, is that they have many different lives. Okay, so so this is going to be algebraic structure for the space of vector fields. Okay, so remember that the space of vector fields, the notation for that is this symbol. Okay. Okay, so gamma infinity, the infinity means infinitely differentiable. Tm means vector fields on M, so taking values in Tm. Okay. All right, so first let's look at the interplay between functions and vector fields. Okay, so first, oops. The space, and again, I forget if I introduced notation for this, but here it is. Okay, so C infinity of M, which is the set of all smooth functions. So functions means real valued functions. On M. Okay, has the following algebraic structure. Okay, so first of all, it is a real vector space. Okay. Okay, so it has the structure of a real vector space. All right, so I need to tell you what the vector space operations are, and they're the obvious ones. So you've seen function spaces before, right? So spaces of functions in some detail in previous courses. So function spaces like C0. L1, L2, LP, okay, things like that. So this is of that ilk, and the vector space structure is put together in the same way as it is for those kinds of spaces, and that is that F plus G, if I take two smooth functions F and G, and I want to add them, I need to tell you what that is evaluated at X, and of course it's this. Okay, so that's vector addition. And then if I take a scalar alpha and multiply it by a function f, that's alpha f of x. Okay, so that's the vector space structure. So you're familiar with that. Okay. It also has the structure of a ring. Okay. And so the ring structure, so I don't know if you're familiar with the notion of a ring. A ring is an algebraic, a space with an algebraic structure which has two operations, addition and multiplication. But the multiplication, so the addition is going to be the same as addition here. And the multiplication is not going to be multiplication of a function with a scalar, but it's going to be the multiplication of two functions. Okay, so a ring has those two operations. It has an addition and a multiplication, and we're going to define those operations, and the multiplication will be commutative. So this is what's known as a commutative ring. Okay, and so the ring operations. Okay, so I need to tell you again how to add two functions, but we know how to do that already, and it's the same. Okay, then I need to tell you how to multiply two functions, and of course, you do that in the obvious way. Okay. Now, of the spaces that you've seen before, the various kinds of function spaces that I talked about, not all of those are rings, right? So C0 is certainly a ring. If you take the product of two continuous functions, you learned in 280 that that's a continuous function. Sorry, 281. But for example, if you take two functions in L2 and you multiply them together, you don't get a function in L2. Actually, you get a function in L1. Okay, so the ring structure here isn't just kind of automatic in some way like it is with the vector space structure. It's the result of the fact that if you take two infinitely differentiable functions, the product is infinitely differentiable. Okay, so that's, I suppose you don't have trouble believing that, and you've probably even seen that for the first derivative, and it sort of holds recursively for the higher order derivatives in some way. Okay, but in any case, you have a ring structure on the space of smooth functions. Okay, so and so these two things together. Okay, and notice that. All right, so this addition operation is the same. Okay, and this operation and this operation, they're unique to the ring structure and the vector space structure. But the fact is, of course, that this product and this product, they interact in nice ways, right? And so, for example, you have, so I'm not going to go through carefully all of the kind of axioms here that you need to verify, but for example, you're going to have alpha f g is equal to alpha f g, right? Things like that are just obviously true. And so there's an interplay between those two structures, and there's actually a name for the situation where you have a vector space structure that interacts well with a ring structure, and it's called an algebra structure. So together, these things make the set of smooth functions into what's called a real algebra. Okay. All right. Okay, good. So that's just name calling, right? There's nothing there that surprises you. I'm just telling you that the things that you already know, they have a name. And they correspond to more general kinds of algebraic structure called, vector spaces, which you know about, rings, which I don't know if you know about or not, and algebras, which I'm almost certain you don't know about. Okay, all right, good. Now, what about vector spaces? Okay, so now, so we've now put some algebraic structure, on the space of smooth functions. Okay, now let's look at algebraic structure on the space of vector fields. Okay, gamma infinity of Tm, okay, which is the space of smooth vector fields on M. Okay, that also has some algebraic structure. And again, this, when I write down this structure, it's not going to shock you, right? It's kind of obvious if you think about it, but it's there, and you need to make the observation that it does have this structure. Okay, so it has the following algebraic structure. Okay, so first, like the space of functions, it has a vector space structure. Okay, and that is given in a fairly obvious way. Okay, so if I take two vector fields, x and y, okay, so to add them, I need to give you a vector field. So I need to tell you, a vector field is a mapping from M into Tm. So I need to tell you what this does to a point x in M. And again, it does the obvious thing. Okay, so this addition, okay, this is addition in the vector space T, X, M, right? So in a homework, you showed that the tangent space has a vector space structure. So on the right-hand side, when I'm defining this vector space operation, that's the vector space structure that I'm using there to define addition, okay? All right, so again, it's the obvious thing. And then similarly to multiply a vector field X by a scalar, alpha, it's the same thing. Okay, and this is scalar multiplication, again, in the vector space, which is the tangent space at X. Okay, and so the point is that the vector space structure for the space of vector fields comes from the vector space structure for the tangent spaces. Okay. All right. Now, vector spaces can also be multiplied, not just by scalars like I've done here, but they can also be multiplied by functions. So if I give you a vector field and a function, you can take the product of those. And again, and when I write it down, you're going to say, of course. But so I'm not doing anything that's supposed to bowl you over, but except just calling things various names. Okay. And so that structure has a name. And what's the name of that structure? The name of that structure is that it's a module. It's a module over a ring, and the ring is the ring of smooth functions. Okay, so this is the name for this structure. And this structure is rather like a vector space structure, except in a vector space, your multiplication is done by scalars, which are from a field, say the field of real numbers or the field of complex numbers, okay? For a module structure, the scalars aren't from a vector space, but they're from a ring, okay? And the ring here is going to be this one that I've defined up here. All right, so what's the ring, the module structure? But and the structure is, like I said, rather the same as that of a vector space. You have two operations, an addition, which of course is going to be the same as the addition for the vector space structure, and then a product. And the product is of elements in the module, which in this case is the space of vector fields, multiplied by elements from the ring, which in this case is the space of smooth functions. Okay. All right, so writing all that down. Sorry. Okay, so the addition is the same as for the vector space structure. Now, I'm going to take a vector field and multiply it not by a scalar alpha, but by a function f. Okay, and you have to define what this is, and what else could it be except this. Okay, and now this makes sense, right? This product right here, again, so when I evaluate f at x, that now just becomes a scalar. And when I evaluate x at x, I get a tangent vector at x, so an element of this vector space. And so I'm going to use again here the scalar multiplication in the tangent space. Okay, so this is scalar multiplication. In the tangent space. Okay. All right. So that's the algebraic structure of functions on one hand and vector fields on the other hand, and the way that they interact through this so-called module structure. Okay. All right. Okay, so now, why did I do this? Why I did this was because what I'm going to do now is I'm going to give an alternative characterization of vector fields. Okay, so what we saw when we talked about vector fields, and we derived those from the notion of a tangent vector, was that curves were the big thing there, right? So when we defined a tangent vector was an equivalence class of curves. All right. And then from tangent vectors, we built vector fields, because a vector field, after all, just assigns a tangent vector to every point. Okay. Now we're going to take a different point of view of what a tangent vector is. Okay. All right. So this relies on the notion of what's called a derivation. So, and again, this is going to be completely familiar to you. But we're just sort of doing it in a slightly more abstract setting than maybe you're used to. All right, so a derivation. All right, so I'm going to give you the specific definition for the setting that I'm working with here. These definitions can be given for general objects, but I'm just going to do it for the things I'm interested in here, which are functions and vector fields. Okay, so a derivation of the space of smooth functions is a real linear map, and I'll call a derivation theta, from space of smooth functions to itself. Okay, and so here, I'm using the fact that I can make real linear maps make sense because above I defined vector space structure there. Okay, so it's a real linear map theta satisfying basically what amounts to the product rule. Okay, so the condition is that theta, right? So theta is already linear, right? So I know that, for example, theta of f plus g is theta of f plus theta of g, and I know that theta of alpha f is alpha theta of f, right? That's just linearity. The thing that I'm interested in here is what's theta of fg. How does it interact with the ring structure, the product in the ring structure? Okay, it's theta of fg. Okay, and the way it does this, and so it's called a derivation, right? And so you think it's probably has to do with derivatives in some way. Okay, and so it does. And if you think this is some kind of a derivative, then it's pretty clear what the definition, what requirement you should make of the definition. And what do you think that might be? The product rule, right? And so the product rule should hold. And that means that if I apply theta to the product, I fix one and sort of apply theta to the other, and then I fix the other and apply theta to the one, right? So it's theta of f g plus f theta of g. Okay, that's sort of some version of the product rule. Okay. Okay, so that's the notion of a derivation. And so there's a more specific thing that you can define. And so that idea of a derivation can be applied to any algebra. Okay, so, so I could replace C infinity of M with any algebra. This definition makes sense. Okay, this definition is specific to functions. Okay, so a derivation at x in M is a mapping, and I'll again call it theta, from C infinity of of M to, in this case now it's going to take values in R, and it's so sorry, and again this is a real linear map, like it was above. Okay, so it's a real linear map that satisfies a rather similar formula to the one above, except now I'm going to be just evaluating everything at x. Okay, so it's theta f g is theta of f of x times g of x plus f at x theta of g of oh, I apologize, I don't need the argument there. This one you don't need the argument, okay, because it's already a scalar. So sorry, let me just rewrite that because it's messy. Okay, so it's theta of f g of x plus f of x theta of g. Okay, now, okay, so why do I introduce these concepts? I introduce these concepts because they give me alternative ways of talking about, oh, sorry, I don't know what, thank you for asking me to do this now. Okay. These concepts of derivation give me alternative ways of defining a tangent vector, and it gives me alternative ways of defining vector field. Okay. All right. So to every derivation theta at x, okay, there exists, sorry, there exists a tangent vector, a unique tangent vector, which I'll call Vx, at the tangent space at x, such that theta of f is equal to df at x paired with Vx. Okay, so remember the df, so df is an element of the cotangent space. Okay, and Vx is, of course, as I just said, an element of the tangent space. Okay, and our notation here simply means that you take this cotangent vector, which by definition is a linear mapping on here, and you apply it to that tangent vector. And the result is therefore a number. Okay, and so what this tells us is that you can alternatively view tangent vectors in this way. Okay, and there's benefits to viewing tangent vectors in this way. And if you pick up various books who do things differently than I do, and they exist, you will see that the definition of a tangent vector is that it's a derivation at x. Okay, and the fact is that the two definitions are equivalent. All right. One of the benefits of doing things in this way is that this immediately gives you a vector space structure for the space of tangent vectors. Now, if you think about the homework problem where you proved that the tangent space had a vector space structure for our definition of tangent vectors, it's kind of gross, right? You have to choose coordinates and define addition and scalar multiplication in the coordinates, and then you have to show that that definition is independent of coordinates, right? So it's rather non-direct. Okay. Here, the space of derivations, you can verify, automatically has a vector space structure. Okay, and so this makes it immediate that the tangent space is a vector space. The drawback, I think, of the derivation definition of a tangent vector is that you don't have quite the intuition, I think, that you do when you think of tangent vectors as being equivalence classes of curves. I think that notion of tangent vector is more intuitive. Okay, but the fact of the matter is the two constructions are equivalent, and so you can use them one in place of the other. Okay, that's fact one. And fact two is the same kind of a fact, but now for vector fields and derivations, not for tangent vectors and derivations at x. Okay, to every derivation theta, okay, and I don't mean derivation at x, I mean derivation in the first sense of my definitions here, not the second one. Okay, so to every derivation theta, there exists a unique vector field, x, such that, all right, and the condition that you invoke is very similar to this one, except rather than having a single tangent vector at a fixed point x, you're going to stick in here the value of the vector field capital X at x. Okay, so such that theta of f okay, and this. Just to make sure we distinguish it from the previous definition, this has to hold for every x. Okay. All right, so again, this gives us an alternative and algebraic way of thinking of what a vector field is. So a vector field is an operation on functions, okay? And this, okay, so what we know then is for x in gamma infinity of m, we have a derivation theta sub x, okay, and theta sub x is simply defined by that formula, okay. And we call this the Lie derivative with respect to x, capital X, and denote it by L sub x, for L for Lie derivative. In the same way that pronouncing Euler as Euler is a death sentence, pronouncing Lie as lie is also a death sentence. So with excuses given to the person who came up to me yesterday who talked about the Euler-Lagrange equations, I hadn't issued the death threat then, so that doesn't count. Okay. So it's Euler and Lie. So Euler is Euler, who's done lots of things, including the Euler number E. Lie is Sophius Lie, who's I forget, Scandinavian, maybe Norwegian, maybe Danish, I forget. Mathematician from the later part of the 1800s. Okay. All right. Okay. And so we have this operation, and just to sort of punctuate this, we have this operation Lx, which we can apply to every function f, and it's simply going to be the function which you get by doing the thing I described above. Okay. All right, now this should be familiar to you. Okay, so let's make sure that you understand the way in which this thing is familiar to you from vector calculus by writing it out in coordinates. Okay, so it's pretty obviously just going to be, you know, the component vector of x apply, or I should say, the component vector of partial derivatives of f applied to the components of x. So in other words, it's in using summation convention, xj df by dxj. Does that look familiar to you from vector calculus? That's a thing. Do you remember what you called that? Directional derivative, maybe? Yeah, okay. So this is the, in vector calculus, this is the directional derivative of f with respect to x. Okay, and so there's an operation from vector calculus which actually makes sense geometrically, as opposed to, as we saw previously, as opposed to the gradient vector field, which doesn't make sense. The gradient vector field is actually the thing which here we're calling df, and it's not a vector field, it's a covector field. Okay, good. Okay, so carrying on with algebra. Okay, so using the derivation structure of the space of vector fields, okay, namely that there's a one-to-one correspondence between vector fields and derivations. Okay, we can define for every x and y, every pair of smooth vector fields, okay, a vector field x, and I call it x bracket y. Okay. All right, and here's the definition of that thing. So the way I'm going to define this new vector field, x bracket y, is by defining it as a derivation. Okay, by the following formula. So to define a vector field, by my previous remarks about derivations, it suffices for me to tell you what the derivation associated to this new vector field is. So I need to tell you what that is applied to a function f, and the way it works is this. Okay, and you require, of course, this to be true for every smooth function f. Okay, so there's something you have to do here. Okay, so you must show that this is a derivation. Okay, so you need to show, so sorry, I'm going to scroll up here for a second, that it satisfies the product rule, all right? Because that's not immediate from the definition that it does, because, you know, this one satisfies the product rule, but then I'm differentiating it again, and so God knows what happens, and then, you know, I'm doing the same thing, but in a different order. So, you know, it's, so for example, just to make sure you understand that there's something to do here, if you were to define this thing to just be, let's say that, okay, just Lx, Ly, F. That is not a derivation. That does not satisfy the product rule that a derivation needs to satisfy, okay? And the one way to think about it is that this is the correction that you need so that the things that go wrong in the first part are canceled out by the things that go wrong in the second part. All right, so there's actual stuff you need to do to verify that that thing is a derivation, and it's not difficult. You just use the fact that Lx and Ly are themselves derivations, and you do a calculation. Okay. All right, but nonetheless, that thing is a derivation. Okay, so this vector field, this new vector field, x, y, is called the Lie bracket. Of x and y. Okay, so notice a couple things. Notice that it's not commutative, right? So the Lie bracket of x and y is not the same thing as the Lie bracket of y and x. In fact, the sign changes. Okay, so properties of this thing. Excuse me. So as a mapping thought of as a function of both of its arguments, x and y, this is R bilinear. Okay, and so that has the obvious meaning that if you fix a y, then it's linear in x, and if you fix an x, then it's linear in y. Okay, with respect to multiplication by real scalars. It's not true with respect to, for example, multiplication by functions. Okay. All right. So it's not symmetric, but it's skew symmetric, obviously, just from the definition. And then it satisfies some peculiar identity, which is nonetheless extremely important, but for reasons which we won't be able to get around to in this course. Okay, and it satisfies an identity like this: x, y, z. Okay. All right. So you take that triple Lie bracket, and then you just permute its entries. Okay, so plus by shifting them all to the right. Okay, so z, x, y plus y, z, x equals 0. Okay, so there's a peculiar identity that it satisfies. Okay, and you can verify this. So this identity is what's called the Jacobi identity. Okay, and it's important, but for reasons which we will not see in this class. Okay, and so something having these properties is what's called a Lie algebra. In a general sort of vector space having these properties is called a Lie algebra. And so you could say that the space of vector fields is a real Lie algebra. There's much simpler examples of real Lie algebras. So for example, the space of skew symmetric n by n matrices, right? We've seen that before. That's a Lie algebra. Okay, right, so good. All right, so now, so this has been a purely, so last lecture we saw differential equations and vector fields. This time we have algebraic structure of vector fields. Now there's a very deep connection between those two things, which I will now describe to you. So the connection between the bracket and flows, like we talked about last time. Okay. All right. So the connection is this. So let x and y be two smooth vector fields. Define a curve, gamma of t. Okay, and the curve is going to be defined like this. All right. So what I'm going to do is I'm going to start at a point x in M. Then I'm going to take the integral curve of x, and I'm going to follow, I'm going to take the integral curve of x, the vector field capital X, through the point little x for time t. So I'm going to draw a picture here to illustrate this. Then what I'm going to do is, starting with now this initial condition for this given time t, I'm going to take the integral curve of y through that point. All right. Then I'm going to take the integral curve of x, but now what I'm going to do is I'm going to go backwards. So I'm going to go from 0 to minus t. If t is positive, if t was negative, then these are already going backwards. Okay, and then I wrap it up by doing the same thing with y. Okay, now let's take a look at the picture of what that curve looks like. Okay, so I start at x. Okay, this first bit here says that I take the remember what the flow is. The flow evaluated at x takes the integral curve for x and follows it for a time t. Okay, so I'm going to go along here, and I end up at this point, which is phi x t of x. Okay, then this says that starting at this point, I follow the integral curve for y for time t. Okay, so maybe it looks something like that. All right, so this is phi y t composed with phi x t of x. Okay, and then, like I said, I now go backwards. Okay, and so the integral curve going backwards, kind of, and so maybe I'll draw arrows on here just to clarify which direction I'm going. Okay, so I go backwards, all right, like so, and so I do this. Okay, so the change in direction of the arrow corresponds to the minus t. All right, so this point will be phi x t, minus t composed with phi y t composed with phi x t at x. Okay, then finally, again I go backwards, but now by y. Okay, so I end up somewhere here, and the fact is you don't necessarily come back to x. Okay, so that point is gamma of t, which is phi y minus t of phi x minus t of phi y t of phi x t of x. Okay, and so the idea is that as you vary t here, okay, I'm going to kind of go for longer or for shorter times, right? Okay, and so you get, for each fixed t, you get a point gamma of t, and then you have a curve like this, which runs through that point. So this is the curve gamma. Okay, does that make sense? Okay, so as t gets, when t is 0, I don't do anything. Okay, and then I allow t to grow, and I follow some curve gamma like that. Okay, so what we're interested in is what is that tangent vector? So in other words, what I told you was, and you can verify this directly with simple examples, you can verify that when you do this, you don't end up at the same point. And so then the question is, what direction do you go for small t? Okay, so that's the question. What direction does this motion go for small t? Okay, well, what that means is what's the tangent vector to the curve gamma, right? Because that's exactly what, you know, the tangent vector to a curve is meant to represent. It represents which direction the curve is going. So your answer should be that it's gamma prime at 0. That's not the answer, unfortunately, and the reason is, so I'm going to call that a guess. Okay, the reason is that that's always 0. Okay, so no matter what x and y do, that thing is 0. So what that means is to first order, right, because that's what the first derivative of gamma is representing, to first order, I go nowhere. So it's kind of like, you know, t squared. Okay, so that's is wrong because gamma prime of t is always 0. Okay, so then your next guess is going to be take the second derivative, right? So just like if you think about the function t squared, right? So the first derivative, you know, whoops, it's when you evaluate it at 0, isn't telling you anything. But, you know, if you evaluate the second derivative, it's positive, and so that kind of tells you you're going in the positive direction. Okay, so the second derivative contains the same information in cases where the first derivative is equal to 0. And I think the answer is, so you can take the second derivative, and I'm going to call that gamma double prime of 0. Okay. And you have to be careful about what that means. So in a homework problem, you will show that if you have a curve, the second derivative with respect to time along the curve is not a tangent vector. Okay, but if you look at that problem, you'll see that the terms in the expression for gamma double prime, which cause that thing not to be a tangent vector, the problematic terms go away when the first derivative is equal to 0. Okay, so actually, this isn't going to be a question in the final exam, but the point is that the second derivative makes sense in cases where the first derivative is 0. Okay. And the answer is this. And I think I have the factor of a half right. Okay. The fact is that you go to second order, right? Because to first order, you go nowhere. To second order, you go in the direction of the Lie bracket of x and y. Okay. Yeah, sorry.
How can you have a non-zero second derivative if your first derivative is always 0?
T squared. Right, so we're evaluating at a single point, right? So the derivative of t squared at t equals 0 is 0. Second derivative is 1. Yeah, okay, yeah.
Why is the first derivative 0?
Do the calculation. So it's not that easy to do, I admit, but it's true. So I'm asking you to just swallow that. Okay. All right. You know, maybe an intuitive answer is this. I know that to first order, I go along here in the direction of x. right? That's what the integral curve does, right? It goes in the direction of x. Now, to first order, then I'm going to go in the direction of y. So now I've gone to first order in the direction of, kind of x plus y. Then I go backwards. So I'm subtracting those things off. So that's not a proof, but that's the intuition. Okay, the proof is actually tedious. Okay, so the point is, though, is that this connects the algebraic structure of vector fields through this Lie bracket to the kind of geometric structure of vector fields that we saw last time as solutions of differential equations. Okay, so these are all very deep and intriguing things. But next time what we're going to do is we're going to talk about affine connections, and we're going to use some of these properties of vector fields in our definitions for affine connections. Okay.